So in this problem, we're going to look at some problems using the same equation, gravitation, and looking at kind of doing it numerically now rather than just seeing the changes. So how you can do it, we start with our equation. Fg equals big G, mass of Earth, mass of a satellite over distance between them squared. So I can start with Fg, plug in what big G is. We saw from before, this is on your formula chart, 6.67 times 10 to the negative 11. Multiply by mass of the Earth, we can see that's here. It's in kilograms, that's correct. So that is 5.98 times 10 to the 24th. Multiplied by mass of the spaceship, again in kilograms, so I'm good. 2,000 kilograms. Divided by the distance between them. Okay. Here we can see it says the spacecraft orbits 2 Earth radii from the Earth's center. So that is from here all the way to there. And that distance is 2 times the Earth's radius. So I'll do the 2 multiplied by the Earth's radius, which is given here. But we don't want kilometers, we want meters. And I can do some conversions, so that's 6.38 times 10 to the 6th meters. And don't forget this, a lot of people will mess this up. Anytime you have to deal with that distance there, it's distance squared. And that's where I write the equation down. So, put that into your calculator, see what you get. Right. Now, what I want you to do is look at it another way. Because I believe we also know force of gravity equals mg. Right. Now, when I do this, what mass is this? Well, this is the mass that the force is at down. That's mass of the spaceship. That's what we're comparing to. So what I could do is I could just do the same process we did before. Okay. Well, this also equals big G, mass of the Earth, mass of the satellite, over distance between them squared. Okay. Now with this, I can see I have doubled the distance between them. If it was on the Earth's surface, we know what G is, 9.8, but I have doubled that. So here, this would be 2. Anytime I have a distance change, I have to square it. And so this over here is going to be divided by 2 squared, which is 4. Right. So the force of gravity on the object should be 1/4. So you can see if the force of gravity on your object is 1/4. Now 1/4 what? 1/4 the force of the spaceship times G. So I know the force of the spaceship is 2,000. Now whenever you use this equation, it'd be using 9.8 right, times 9.8 divided by 4. Right? And check with this answer that you've seen and see if they're the same. They should be. Practice doing all of this, though, over here in your calculator. If you can't get them to do the same, you may want to come ask me how to do scientific notation in your calculator. Here's another example for you to try. Right? This one says, estimate the effective value of G on the top of Mount Everest, right? Which is 8,850 meters above sea level. So I had to draw a picture. Okay? I have the Earth, okay? And it says Mount Everest, again, not drawn to scale. This distance right here is 8,850 meters. Okay? But we know it's the distance between the two centers. So if someone is at the top of Mount Everest, that would be the distance of the radius of the Earth away plus this distance. So that's their total distance. Okay? So if I was looking at my equation, I would say, well, force of gravity equals big G, mass of Earth, mass of the person, whatever object is up there. Right, let's call that mass of the person, divided by distance between them squared. But it doesn't want the force of gravity, it wants the acceleration. So we could say this is the mass of the person times G. Okay? Doing some algebra, divide mass of P to both sides and it cancels out. So here, little g equals big G, mass of the Earth, over the distance between them squared. Okay? Now, I don't know how much this changes the distance between the two. It's not like it's doubled or halved, so I'm actually going to have to calculate it. So I could write down my equation. And as you can see down below, I plugged in the numbers so far. Okay. Again, these are both on your formula chart. You'll be able to look them up. Now the other one I have to do is get the distance. Okay. How would I write this distance? Well, it is the 8,850 meters plus the radius of the Earth, which I saw in the problem above. That is the 6.38 kilometers. Again, practice. Make sure you can do this conversion on your own. 6.38 times 10 to the 6th meters. And then I have to square everything. Take a second, see what you can plug into your calculator, and you get. When I did this problem, I got 9.78 meters per second squared. So the acceleration does become a little less, but as you can see, not a whole lot, even on Mount Everest. Okay. If you want, you can give another shot for calculating it for the International Space Station. Try and use 270 as that distance, and then we can look over that in class together if you want to see what that one is. The next problem, right, we have a hypothetical planet. It has a mass of 1.66 times that of Earth. What is G near the Earth's surface? Well, we saw you can do little g equals big G, mass of Earth, over r squared, and you could plug in the numbers for that. Or we could do our other strategy we practiced a lot now. I could say that the mass is 1.66 times the mass of the Earth. So then I also have to here put a 1.66. If we were using 9.8, we'd get a value, or if we use 10 here, we would get, this is 1.66 times 10, and that would equal 16.6 meters per second squared. So we've seen a lot of calculation problems. Now we're getting to some explanation ones as well. You'll also see ones like this on free response. So in this one, it says we have 3 objects, each with mass m, so they all have the same mass. And we can see they all have the same distance, right? The distance between those two is 2 boxes. The distance between these is 2 boxes. Okay? So let's draw a free body diagram on B. What are affecting B? Well, the first force I have affecting B is the force of gravity of A on B. The other one I have is the force of gravity of C on B. Okay? How do those two compare? Well, we said they have the same mass, same distance, so those will be the same. Now, if I have, these are vectors, so hopefully you know, remember, you add vectors, okay, tip to tail. So the first one I have is force of gravity of A on B. The next one, adding it tip to tail, it is going down, and that is the force of C on B. The resultant goes from the beginning to the end, okay? And so that is my resultant. Okay? The direction it's going is here. That is the net force, adding up all of the forces. The next problem, to solve that, what I want you guys to do is on each object, draw the net force. I'll do the first one, then pause the video and try it on your own. So the first one on A, I have the force of B on A, and I also have the force of C on A. Like I said, pause and check out the other two. So here's what I have for mine. For the middle one, force of A on B here, force of C on B, force of B on C, and force of A on C. Now we need to try and calculate them. I wrote down the equations for all these interactions. So I have A on B. So that covers this. Then I also have force of A on B here. So that's the equal and opposite, same one. Force of A on C, that covers this. Force of A on C, that covers this. Okay? So this equation is good. The last equation, force of C on B, well, that's covered here. And the force of B on C, so we've covered all the forces. Now I can calculate them. So the first one, let's look at force of B on A. So this first one up here. So let's see. The first one has just mass M, so we'll leave it as M. The other one has mass 2M. So this mass is 2, so the force of gravity on this one is 2. Okay, so this force is 2Fg to the right. The distance is just distance d, so I don't need to change that. The next one we need to look at is C on A. Well, that's down here, this equation. Okay. So the mass of A, we said, is right here, 2m. So this is 2. Now here, you got to be careful. The distance between them is d plus another d. So that's a 2. But anytime it's with the distance between them, we have to square that. So this side gets a force. So this force is 1/2 Fg. So the same thing, Newton's third law. If C on A equals 1/2, A on C also equals 1/2 Fg. Now I also left one out. We said B on A is 2Fg. So here, up above, this is 2Fg. So all I have left to calculate is C on B and B on C. So go to the bottom. Mass C is just mass M, so I don't change that. Mass B, that's also just mass M right here and here. So those don't change, and the distance between them is just d right here. So that one doesn't change. So this up here is just Fg, and this here is Fg. Now, let's redraw that real fast. So if I looked back just to this one, right? Object A, I can see object A has 2 times Fg to the right. That is B on A. And then the other one that I have is 1/2, and that is C on A. So those are the two forces acting on A. How would I add those vectors? Well, I have 2Fg plus 1/2 Fg, so this becomes 2.5 Fg. The next one, B, you can see I have 2Fg to the left because based off of Newton's third law, this is B on A. That's equal and opposite to that one. Okay. If I added these vectors, I would end up with 2 minus 1, so this is just Fg. The very last, right, we can see that Newton's third law, this force has to equal and opposite to this one, Fg. And again, Newton's third law, this force is equal and opposite to this one. So here I have Fg plus 1/2 Fg, so that is going to give me 1.5 Fg. So my ranking is going to be A is greater than B, greater than C, which is greater than B. Okay, my explanation will be showing my equations, the work of how I got there. This last problem we'll work on together in class, so don't worry about doing that one. But remember, come to class with questions that you've worked on with gravitation, the multiple choice questions I gave you, or questions from this video. Good luck working on the homework over your break.